Hello, check. Just confirm me once whether I am audible or not. Just confirm me once whether I am audible or not. Just confirm once whether my voice is audible or not. Whether just confirm it once whether it is audible or not. So, a very good afternoon, everyone. Myself, Prateek Mishra, and I welcome you all to the YouTube platform of IMS GATE Academy. We are ongoing through the foundation course of strength of material, and we have discussed pretty a lot of basics, how we see stress, how we feel stress, and how we actually calculate the different values of stress. Then we have also seen how to calculate the elongation, and we have also discussed about the elastic constants. Okay. Moving on to the next phase of our first chapter of strength of material, that is temperature stress. Now, my dear students, the common confusion between temperature stress is student does not feel how the temperature stress is getting introduced in a particular material. As the name says temperature stress, so obviously due to change in temperature, there will be some deformation happening to the body. When these deformations are restricted, the temperature stresses are developed. So the entire theory of temperature stress we will going to discuss today, right? We will going to see the basics and we will going to feel how temperature stresses are developed in a particular body. So let's begin this session with the topic of temperature stresses, right? Okay. So if you have a normal bar of length L, right, it is very much clear to us. If we increase the temperature, the length of the bar will going to increase. Or I'll phrase it in the other way. And the manner in which I am phrasing my statement, you should keep a clear check on that. With increase in temperature, all the dimensions of a material will going to expand, right? Every dimension of the material expands with the increase in temperature. For suppose here we have a material of length L. The height of the material is H and width of the material is B. Width of the material is B, right? I'll just take another color. The height of this material is H and width of this material is B. So this is H and this is B. So from the basics we know that if we increase the temperature of a particular body, all the dimensions of the body will going to expand. And this length will increase to L dash. This is the new length of the body. This is the new length of the body. This height will also going to increase to H dash. And this width of the body will also increase to B dash. So with the increase in temperature, all the dimensions of a particular body will going to increase. Similarly, if we reduce the temperature of a particular body, then all the dimensions will going to contract. It will going to decrease. So if initial length of the body is L, height is H and width is B, with decrease in temperature, that is if you reduce the temperature, the length of the body will also going to decrease, height of the body will also going to decrease, width of the body will also going to decrease, right? So now the new length will be like L double dash, this is L double dash, this is the new length of the body, and clearly this new length of the body is less than the original length. This H double dash is the new height which is less than H, and this B double dash is the new width which is less than this B. So if you decrease the temperature for a particular body, for that your length will decrease, your height will decrease and your width will decrease when you decrease the temperature. Similarly, when you increase the temperature, all the entities or all the dimensions of the body will going to expand. Now the factor or the coefficient which governs this, that by how much amount a particular body will going to contract or expand, is termed as coefficient of linear expansion. So the quantity through which this decrease in length or increase in length is decided, that quantity is known as coefficient of linear expansion. It is known as coefficient of linear expansion. And it is termed as alpha. This alpha decides by how much amount the length of the material will going to increase with increase in temperature, or by how much amount the height and the width of the material will going to increase with the increase in temperature. Same thing, this coefficient of linear expansion also tells us by how much amount with the decrease in temperature the length will going to decrease, or the height will going to decrease, or this width will going to decrease, right? Now the thing is, how we calculate this increase in dimension with the increase in temperature, right? We will going to discuss everything with the increase in temperature, and same analysis is applicable for the decrease in temperature also, right? So with increase in temperature, the free expansion of the bar, that is, if you have a bar like this, if you have this bar like this, right? With increase in temperature, the length of the bar will going to increase. So this is your original length L dash. This is your original length L. This is your increased length L dash. And this happened due to increase in temperature. Increase in temperature. And this increase in temperature is delta T. Delta T is the increase in temperature. So this increase in length of the bar, this increase in length of the bar, delta L, this increase in length of the bar, delta L, can be calculated. This increase in length of the bar, delta L, can be calculated as, so increase in length or change in length is equals to delta L, which is equals to L alpha delta T. So change in length is equals to delta L, which is equals to L alpha delta T. So with the increase in temperature, this change in length depends on the coefficient of linear expansion alpha and the change in temperature, and also on the dimension. Similarly, if we want to calculate the change in height or the increase in height, that can be also calculated similarly. So change in height, delta H is equal to H alpha delta T. This is the change in height or the increase in height due to the increase in temperature. Similarly, we can also calculate the change in width. So change in width which is equal to delta B. This is equal to B alpha delta T. So with the increase in temperature, your dimension will going to increase, and this is how you calculate the change in all the dimension. So the change in a particular dimension with the increase in temperature depends upon the original dimension, then coefficient of linear expansion alpha, and the change in temperature. And it is pretty much clear that if the temperature is increasing, the dimension will also going to increase. And if the temperature is decreasing, the dimensions will also going to decrease. That is, the material will going to contract. I think this is very simple to understand. So this is the change in length, right? So change in length is equals to L alpha delta T for length. For height, it is H alpha delta T. And for B, it is B alpha delta T. So these are the change in dimension. Now, what are the different values of this alpha with different values of the material, with different types of the material. So here is the table that I have included, which gives us the detail about the coefficient of linear expansion for all the materials. That is the common materials that we usually see in the examination. For aluminium, this alpha is like 23.1. For brass, it is like 19. For copper, it is like 17. For gold, it is like 14, and so on and so forth. I have included common materials and their coefficient of linear expansion. And why I did this? To give an idea about the relative expansion between two materials. This table will be useful to analyze which material will going to expand more. So if a question is there in the examination regarding that whether copper will going to expand more or aluminium will going to expand more, so the common factor which decides this will be the coefficient of linear expansion. For the material having more value of coefficient of linear expansion will going to show more change in dimension, for both for increase in temperature or decrease in temperature, right? So if you have to compare between, there is aluminium and there is copper, which material out of these two material, aluminium and copper, which material will going to expand more? So simply you have to look into the coefficient of linear expansion for aluminium and coefficient of linear expansion for copper. Here it is clearly visible that the coefficient of linear expansion for aluminium is more. Hence, the change in dimension for aluminium will also be more. So, aluminium will show more change in dimension as compared to copper. And this is how you have to compare between two metals if a question is there in the examination based on what will be the change in dimension, right? So, this table will be useful. You can just take the screenshot of it. I have added one more detail, that is the Young's modulus. Need not to keep a check on this, because usually in the examination if a question is there, both these values will be given to you. But just for the sake of comparing, you should remember certain values of Young's modulus and also for your coefficient of linear expansion, right? Now I would like to add one more point here, which is a kind of analytical point, okay? This coefficient of linear expansion will going to tell us by how much amount a material will going to show change in dimension with the change in temperature, right? Or I can also frame it like this: with the change in temperature, what will be the change in dimension for a particular material will be governed by coefficient of linear expansion, right? Now coming to this very important kind of parameter which is known as the Young's modulus. Young's modulus tells us how strong the material is. More the value of Young's modulus, more will be the strength of the material. Okay. So if you need to compare between two materials and you have to say which material will be more strong, so simply you have to compare their Young's modulus. The material having more value of the Young's modulus will be having more internal strength. Okay. So Young's modulus indirectly also tells us about the strength of the material. For example, if you have to compare between two persons, you have two persons. This is person A and this one is person B, right? So person A has more muscular power, it is having more height, right? And person B is having less muscular power and it is also having less height, right? So when you have to compare between strength of two persons, you actually compare their muscular power and their flexibility, right? Similarly, whenever you need to compare between two materials, so in order to compare the strength of two materials, so you have to compare between the strength of two materials. Say you have material A and material B. This is material 1, material A and material B. And you need to compare which material will be more strong. The parameter that is used is Young's modulus. The parameter used will be Young's modulus. And Young's modulus is EA and EB. So simply whichever material has more value of Young's modulus will be more strong. So more the value of Young's modulus, material will be more strong. More value of Young's modulus, material will be more strong. Material will be more strong, right? And similarly, alpha tells us about how easily the material can change its dimension with the increase in temperature, right? So if you need to compare between two materials, whether which material is more temperature sensitive. What do we mean by temperature sensitive? Temperature sensitive means with the change in temperature, how much the change in dimension for a material is happening. So if we need to compare between material A and material B, and we need to decide which material is more temperature sensitive, so we will decide using their coefficient of linear expansion. We will decide using their coefficient of linear expansion. For the material having more value of coefficient of linear expansion will be more temperature sensitive. That is, with the slightest change in the temperature, they will going to show more change in their dimension. So coefficient of linear expansion, this is coefficient of linear expansion. This is coefficient of linear expansion that has to be compared if we need to compare between two material with respect to their temperature sensitivity. So, in order to compare which material is more temperature sensitive, so you have to compare through their coefficient of linear expansion. Similarly, if you need to compare the strength for two material, you have to go for the Young's modulus. Okay. Now, if I say which material will going to push the other one. For example, if there are two materials connected like this, if there are two materials connected like this, right? I am taking you to the next level of analysis of temperature stresses, which I don't think anybody in the country will going to teach. Just observe this. You have two materials placed side by side, right? And these two materials are like fixed with the support. I haven't taught you anything about temperature stresses. I'm just focusing on your analysis part, right? Now the question is, the Young's modulus for this material A is EA. This is EA. And alpha for material A is alpha A. Similarly, for material B, Young's modulus is EB and coefficient of linear expansion is alpha B. So you have material A and material B in front of you. If I say EA is more than EB, EA is more than EB. It means that the Young's modulus for material A is more than material B, which means that material A is more stronger than material B, right? Your material A is more stronger. Your A is more stronger than B. Your material A is more stronger than B, right? Now I also say that coefficient of linear expansion for material A is more than material B. What I say? I say coefficient of linear expansion for material A is more than material B. What it means? It means that with the increase in temperature, material A will show more change in dimension than material B. Okay. Material A is strong, material A is more temperature sensitive, right? Whereas material B is weak and it is less temperature sensitive. Just imagine two persons standing side by side, two persons standing side by side. This person A is strong than person B, and also it shows more change in temperature than this person B, right? So what this person A will do, this person A with his more strength will try to pull this member, on the right side, right? This member A or material A with more strength and more temperature sensitivity, it's try to pull this material B on the right side. This material A will apply huge amount of force and will going to pull material B on the right side. So this junction which is there, this junction will going to shift towards right. This junction will going to shift towards right. And how we have decided this? We have seen what are the comparable strength of these two materials, means which material is more strong and which material is having more value of alpha, right? So this is one of the simplest case where material A has more value of Young's modulus and more value of coefficient of linear expansion. That's why we can very easily say this, that material A will going to push this material B on the right side. But if some other relation happened, like you are given with some different relation where EB is more than EA. So if this kind of relation was given, EA is less than EB, and alpha A is more than alpha B. If this kind of relation would have been given, then we directly cannot say where this junction will going to move. We have to actually calculate the deformation and then only we can say where this junction will going to move. So for this case, we need to go for calculation. We need to go for calculation of deformation. Then only we can say where this junction will going to move. But for now, as we know that for material A, both Young's modulus and coefficient of linear expansion is more, so we can clearly say this, that your junction will going to move on the right side. This was gate 23, one of the option that was there. Same kind of materials were given, same junction was there, this kind of relationship was given to us, and we need to determine this junction will move to the left or to the right, right? So when such kind of condition is given to you, it is very easy to identify where the junction will move. So a material with more strength, having more value of coefficient of linear expansion, will try to push the member, right? Sorry, this is not pull, this is push the member. This material A will going to push the member, this will going to push the member. This material A will going to push material B, and this entire junction will move towards right. The junction will move towards right. So your junction will move towards right, right? So this is how you should analyze when two different materials are given to you and such kind of statement is there. This was gate 22, one of the statement which was there, right? Okay, so I hope this is clear to you. Let's move on with this. So these are the certain examples where you can see the effect of temperature. First one is deformation of steel railways. You might have seen when these rails are laid, for suppose these are the rails which are laid like this, right? Like this, your rails are laid. So at certain distance, you will see certain openings that are present in these rails. At certain distance, these kind of openings which are present, these openings are provided in order to account for the change in length due to increase in temperature. Due to high temperature, this length of the rail, this length of the rail will going to increase. This length of the rail will going to increase. So this is my plan that I have drawn. This is the plan view. If you look into the cross-sectional view or the side view, you will find that if this is my rail, certain space is given in between. And why this space is given? Due to increase in temperature, in order to account for this change in length, right? In order to account for this change in length, so that these two members does not overlap each other. If this gap would not have been provided, what could have happened? For suppose if the rails are laid like this, if the rails were laid like this, connected to each other, if the rails were laid like this, without any proper gap. So with the increase in temperature, the length of the bar will also going to increase. And if both the length will going to increase, they will going to just show this kind of deformation. They will going to just overlap each other. This is the overlap that happened. This is the overlap that happened. And if such kind of overlap happened, this leads to the damage of the railway track, and it also will going to lead to certain accident. So this kind of overlap we do not want. So this is the overlap that happened. This is the overlap of rail that happened, and we do not want this. We do not want this to happen. We do not want these rails to overlap one another, because this overlap will also damage the railway track. Overlap damages the railway track. Overlap damages the railway track. Which leads to accidents. Right. So this kind of temperature change, in order to account for this kind of temperature change, we basically provide certain amount of gap between the two rails. So every time we provide these gaps in order to account for this change in length. Because if this gap was not provided, then what will happen? These rails will going to overlap, and due to this overlap, right, it will directly lead to the accidents of the trains. Next one is cracks in the concrete footpaths due to heat. This we have already seen that with the increase in temperature, right, the concrete will going to show certain amount of expansion, and due to this expansion, again the concrete blocks will overlap each other, and that lead to the development of cracks. So these are all the examples that are there. One more example is slack in the power transmission line. So what do you understand by slack? Just understand this. When the poles are wired, this is my pole A. When these poles are wired, right? This is my pole A and this is my pole B. So initially, you will see the transmission line connected like this. So this is the usual connection of the transmission line. But with the increase in temperature, this transmission line will going to slack like this. You will see a huge amount of deformation happening in the entire length of this transmission line. So this deformation that happened, due to which transmission line just deforms in the downward direction, this is known as slack in the transmission line. This is known as the slack in the transmission line. That is, by how much amount the transmission line has deformed and its height has reduced from the surface. So this is the slack in the transmission line due to the increase in temperature. It is very much clear that with the increase in temperature, the length of this transmission line will going to increase. Why? Because this transmission line is also made up of metals like aluminum and copper. So with the increase in temperature, this length of the transmission line has increased, and this length actually creates the slack in the transmission line. So we do not want this to happen. That's why this length or this distance between the two poles are designed appropriately in order to account for that slack. We do not want these transmission line to touch or reach the population that are residing on the surface. Because if such kind of thing happened, it will lead to usual accidents in day-to-day life. So these two poles are designed in such a way that this lag should not be huge, that directly affects the life that is there residing below the transmission line, right? So these are few of the examples of temperature deformation due to increase in temperature. Now moving to the most important topic, how the temperature stresses are developed, right? Till now we haven't discussed anything about temperature stress. Even we haven't said any word like temperature stress till now. Now the topic of discussion is temperature stress. So my dear students, first of all you need to understand how these temperature stresses are developed in a material. Then only we can decide how the temperature stresses are calculated, right? So I'll begin with this. You have this material of length L. The length of this material is L, right? With the increase in temperature, the length of the material will also going to increase. This is the change length of the material. This is the increase in length of the material. So this total length is L dash. This total length is L dash. This change in length is delta L is equal to L alpha delta T, right? Simply what I did, I took a material in which I have increased the temperature. So due to this increase in temperature, this material has expanded freely. There is no restraining happened for this material against this expansion, okay? So if no restraining happened or the resisting force is not applied over the body, the stresses will not develop. So this is my free expansion. This is my free expansion. And in free expansion, there will be no development of stress that actually happened, right? So under the case of free expansion, no stresses will develop because there is no restraining force present in the body. Now observe this. This is your material, and this material of yours is restricted on the either side. I'll just be back in 1 minute. So, very good afternoon. Okay. So, we are discussing about temperature stresses. Okay. My voice is audible, right? Very good afternoon. Very good afternoon, Prateek sir. Very good afternoon. Okay. So, what I said that if you just take a material and increase the temperature, simply the length of this material will going to increase, but there will be no development of stresses in the material, right? So, this change in length is termed as free expansion. Now, observe this. You took a material, and for this material, just 1 minute. You took this material, and this material is kept within the supports, right? This material is restricted from these two supports. You just place that material in between these two supports. Now what will happen is, when you increase the temperature, this material has a tendency to expand. This material has the tendency to expand freely. But these supports will not allow the material to expand. These supports will try to compress the material. The nature of the material is to expand with the increase in temperature, but these two supports will try to compress the material and does not allow this free expansion of the material. So the supports restricts free expansion. Supports restricts free expansion. And when these supports restrict free expansion, these supports will try to compress the material like this. These supports will try to compress the material. These supports will not allow the material to expand freely. Due to this compressive force provided by these supports or applied by these supports over the material, there will be the temperature of stress. There will be the development of stress in the material. And this stress, which is developed due to the compressive force provided by the support, this stress is known as the temperature stress. This stress is known as the temperature stress. Now, I hope this is very much clear to you. What actually happened? We restrict the material between the two supports. Okay, and we increase the temperature for this material. If these supports were not present, this material could have freely expanded to this new length. But these supports will not allow the material to freely expand. These supports will try to compress the material, right? These supports will try to compress the material, and due to this compressive force provided by these supports over the material, there will be the development of stresses inside the material. These stresses are known as the temperature stresses. Okay, now how to calculate these temperature stresses? We cannot directly calculate these temperature stresses by the equation of equilibrium. But one thing we know this material is not changing any length. This material is not showing any change in length. Means the total deformation for this material is 0. So total change in length delta L is 0, right? Now observe this very carefully. How to calculate this? This delta L, if we are writing 0, is a combination of two activities. First one is, if we allow the material to expand freely, the change in length will be L alpha delta T, right? So the first effect is the effect of free expansion. Due to free expansion, there will be change in length. But this change in length is suppressed by these supports. And these supports led to the development of temperature stress inside the material. So the first effect is the free expansion, and this free expansion is restricted by the temperature stresses due to the supports, right? Now what I will write is this total change in length, where if I am writing it to be 0, this is the combination of two things. First one is the free expansion. First one is the free expansion. This free expansion will try to increase the length, but this free expansion is restrained by the temperature stress. So I will write minus effect of minus effect of sigma, that is the temperature stress, right? Free expansion can be written as L alpha delta T. This is the free expansion. But this free expansion is restricted by this sigma. If sigma is the stress, then their change in length can be calculated as minus sigma by E. This is the strain multiplied by the length, and this should be equal to 0. And this is how we calculate the value of sigma, that is the temperature stress, right? I am saying do not remember any formulae for calculating this sigma, because this sigma temperature stress will going to change if the support condition is changing. So it's better to understand how to frame this equation, that is the compatibility equation, right? It is always better to understand how to form the compatibility equation than remembering this formula, because this formula you will going to get confused. But if you are able to write this equation correctly, you can very easily calculate this sigma, right? So this is how you calculate the value of temperature stress when your body is restrained in one direction. This is your body which is restrained along x-axis, right? So I'll just write this down once again. So if this is my body, and if this body is restrained in one direction, my body is restrained in one direction. This is x-axis direction, and my body is restrained in one direction, that is the supports are there in one direction. Then in that case, what I will write is total deformation along x is 0, that is delta L is 0, right? But if you look into the other two dimension are still free to expand. There is no restriction of the increase in height and the increase in width. They can freely expand, but only the length is restricted on the either side. So the length will not increase, but your height and width can increase, right? So that is also we can see. So your total deformation along x is 0, which leads to the development of temperature stress, sigma, which leads to the development of temperature stress, sigma. So I can write your free expansion effect minus effect of sigma should be equal to 0. So this is L alpha delta T minus sigma by E into L. This has to be 0. Okay. Now calculating the other two dimension. What is the change in length or change in height? So change in height delta H is equals to free expansion right? So free expansion of height, that is H alpha delta T. Now, there will be the Poisson's effect for this sigma on the other two directions. For y and z, there will be Poisson's effect for this sigma. So, the effect of this sigma on y plus the effect of sigma in y direction. So, this is equal to H alpha delta T plus mu times of sigma by E into H. So, this is your effect of this sigma in the y direction. Now, talking about what will be the change in width. So, similarly, we can calculate the change in width also. So, change in width is equals to pre-expansion plus effect of sigma So free expansion along width is B into alpha into delta T, and the effect of sigma is plus mu times of sigma by E into B. So this is your change in width. Now also your height and width can expand freely. The only restriction is along your length. So this is how you deal with the change in different dimension, and this is how you calculate the value of sigma. From the first equation, you can very easily calculate the value of sigma, and using the sigma, you can calculate the change in height and change in width with the increase in temperature. So this is our case number 1 for thermal stress, where your body is restrained in one direction. Now moving to the next topic of discussion is when the body is restrained in two direction, how to calculate the thermal stresses and what will be the effect of thermal stresses on the body. Okay. So case number 2 is body restrained in two directions. Body restrained in two directions, right? So I'll just quickly draw this body. So this is my first support. This is my first support. And this is my second support, right? So this is how you restrained the body along x direction. This is your direction x. This is your direction x. Then restraining the support along y direction, right? So these are oh, I'll draw this figure like this. So it is restrained along x direction like this. And it is also restrained along y direction like this. So this is my x direction and this is the y direction. In two direction, this body is restrained. In two direction, this body is restrained. Free expansion of the body is not allowed in two direction. The thermal stress developed along x direction is termed as sigma x. This is termed as sigma x. And the thermal stress developed along y direction is termed as sigma y. No doubt both these thermal stresses will be same. Your sigma x will be equal to sigma y. Sigma x will be equal to sigma y. But in order to give the clarity, I have just mentioned sigma x and sigma y. Any type of temperature stresses will be same, right? These temperature stresses will be developed along the length and these temperature stresses will be developed along the height. Okay, now how to analyze this? So the first thing is, if we have restricted this body along x direction, then there will be no change in length along the x direction. So what I'll write, net change in length, net or change in length is 0. Change in length along x is 0. So delta L is 0. This change in length comprises of free expansion, that is, if we haven't provided any support, this material would have been freely expanded, right? So first one is free expansion. This free expansion is compressed or restrained by these supports, which leads to the development of sigma x. So minus the effect of sigma x, Now observe this very carefully. In y direction also, this material is restrained, means this material is not allowed to expand in the y direction. Due to this restraining which is provided in the y direction, there will be thermal stress in the y direction also. And this thermal stress in the y direction will going to have the Poisson's effect on the x direction. So if compressive stresses are developed, these compressive stress in the y direction will going to expand the length of the material in the x direction. So plus the effect of sigma y, right? So this is your net change in length. So net change in length free expansion is L alpha delta t. This is the free expansion. Effect of sigma x will be sigma by E into L. This is the effect of sigma x. Then the effect of sigma y will be plus, because this sigma y is increasing the length, plus Poisson's effect of sigma y, which is nothing but mu times of sigma by E into L. Both the temperature stresses are equal. Sigma x is equals to sigma y, which is equals to sigma. So this is how you actually write the total equation for this change in length along x direction. Similarly, you can write the expression for change in height. Since this support is restraining the expansion of the material in the y direction, again there will be no change in height, and that can be written as, so your change in height can be written as, so change in height delta H This is also equal to 0. This change in height includes free expansion minus effect of sigma y, minus effect of sigma y. You can clearly see from this diagram, if this material expands in the y direction, then these two supports will try to restrict this free expansion, and due to this restriction, sigma y is developed. That's why sigma y is responsible to bring down this change in height for this material. So effect of sigma y. Next one is plus effect of sigma x, plus effect of sigma x. This sigma x is compressive in the x direction, therefore it will going to increase the other two dimension. It can be increase in height or increase in width. So this sigma x has the positive impact on the change in height. So plus times effect of sigma x, and this has to be equal to 0. So free expansion along y direction is h alpha delta t. This is the free expansion. Effect of sigma y is minus sigma by E into h. This is the effect of sigma y. Then effect of sigma z will be plus mu times of sigma by E into h. And this has to be 0. So this is how you calculate the total change in height for a body which is restrained in the y direction, right? And from here you can very easily calculate the value of sigma. Okay. So this is the effect change in height, right? Now moving to the third dimension, change in width. Change in width. That is delta B. Now this delta B we need to calculate because along the width, the supports are not provided and it is allowed to expand freely. So the first thing is, with the increase in temperature, the width of the material will going to increase. Second thing is, there will be the Poisson's effect for the thermal stresses developed along x and y direction. Both of these thermal stresses will also try to increase the width of the member. So the change in width is equal to free expansion plus effect of sigma x plus effect of sigma y. Effect of sigma y. So this is how your total change in width is written. So free expansion is B into alpha into delta t. This is the free expansion. Effect of sigma x is plus mu times of sigma by E into B. Then effect of sigma y is plus mu times of sigma by E into B. So this is the total change in width for this member where it is restrained along x and y direction, right? So this is how you can calculate. Okay. Moving to the last case where the body is restrained in all the three directions. Where the body is restrained in all the three directions. So you have a body like this. And this body is restrained in all the three directions. In all the direction, this body is restrained. In all the direction, this body is restrained. It's like ki inside the box, you have kept the material which is not allowed to expand at all. So, case 3 is body restrained in all the 3 directions. And if the body is restrained in all the 3 directions, there will be the thermal stresses along x direction, along y direction, and along z direction. So in all the directions, you will going to have thermal stresses. So you have thermal stresses along x direction, thermal stresses along y direction, thermal stresses along z direction, which is equal to sigma. You will have thermal stresses in all the 3 directions. So in all the 3 directions, in all 3 directions, in all 3 directions, thermal stresses will be present. Thermal stresses will be present, and the nature of these thermal stresses will be compressive. The nature of these thermal stresses will be compressive. Their nature is compressive. The nature for these thermal stresses is compressive. So these are compressive stresses. Now, how to calculate these thermal stresses? So for calculating this thermal stresses, again we will go with the same type of equation. So the first one is the change in length. First one is change in length. Change in length. Delta L is 0 because it is restricted in the x direction. So change in length is free expansion of length minus effect of sigma x. So this sigma x will try to restrict the increase in length, but the other two thermal stresses, sigma y and sigma z, will try to expand the member. So plus effect of sigma y plus effect of sigma z. And this should be equal to 0, right? So this is the total change in length. So free expansion is L alpha delta T. This is the free expansion minus effect of sigma x, which is sigma by E into mu, sigma by E into L. Next is the effect of sigma y, which is minus mu times of sigma by E into L. Then effect of sigma z, which is again, this is also plus mu times sigma by E into L. So this is how you calculate the value of thermal stress sigma, right? Now, if you need to analyze along the height or in the y direction, that can be done as the change in length, change in height is 0. If you need to analyze along the y direction, change in height is 0. Change in height is 0 because the material is restricted along y direction. Now this change in height is equal to 0 comprises of free expansion along y direction minus effect of sigma x, effect of sigma y, because this sigma y will try to reduce the height of the member. Next, plus the Poisson's effect of sigma x and sigma z, plus effect of sigma x plus effect of sigma z. And this should be equal to 0. So the free expansion of the member is H alpha delta T minus effect of sigma y, which will try to restrict the member from expanding. This is minus sigma by E into H. Effect of sigma x is plus Poisson's effect of sigma by E into H plus Poisson's effect of sigma z, which is plus mu times of E into H, and this should be equal to 0. So this is the analysis along the height. Similarly, if you need to analyze along the width, that can also be done. So along the width also, since the material is restrained in all the three directions, now along the width, the material is also not allowed to expand freely. So the change in width that is delta B is also 0. So this change in width again comprises of free expansion. Now this width is restricted by the thermal stresses in the z direction, right? So free expansion minus effect of sigma z, Then you have Poisson's effect of sigma x and sigma y. And what is the Poisson's effect? Sigma y is compressive and sigma x is also compressive. So it will try to expand the member along the width. So minus effect of sigma z plus effect of sigma x plus effect of sigma y, and this should be equal to 0. Right, so this is free expansion, which is B alpha delta T minus effect of sigma z, which is sigma by E into B. Next, effect of sigma x plus mu times of sigma by E into B plus effect of sigma y plus mu times sigma by E into B. Right, so this is how you actually write the equation along x, y and z direction and calculate the value of thermal stress or whatever quantity which is asked. So this entire analysis is when your body is restrained in all the three directions and the temperature is increased by delta T amount. Your temperature is increased by delta T amount. With the increase in temperature, you will going to have the development of temperature stress along x, y and z direction, right? So this is how basically you frame the equation in order to analyze any question for thermal stresses. So I hope you got this concept very clearly, this fundamental concept of writing the equation for thermal stresses and what exactly and how exactly we feel the nature of thermal stresses. So along any direction, if you have provided a restraint, that is, you are not allowing the material to expand freely, then only along that direction you will going to have the development of thermal stresses. So I hope you have understood the concept very clearly. So that is all for the day. Thank you so much for listening patiently. I'll see you in the next session very soon. Thank you so much.